So we're looking today at lesson 5. Lesson 5 is going to take us through a different kind of transformation, a transformation that is called a stretch. And I'm just going to give you lesson 5 this evening. Hopefully you're checking this stuff out at night. We're looking at stretching the graph. And what does a stretch mean? It means we're going to expand or reduce the graph in relation to one dimension while keeping the other dimension constant. So we're going to stretch x, we're going to stretch y. You'll need your graphing calculator. So we've got two letters that we're going to introduce, the letter A and the letter B. A will stretch y's and B will stretch x's. And like we've seen for the y's, the y lettering can either be on the left-hand side or the right-hand side. If it is read on the right-hand side, we can read its effect directly. If it is read on the left-hand side, we need to operate with the idea of reciprocal. And it's always true for x's, pardon me, that when we manipulate x's, we always get the opposite. So here, as always, we're going to have the opposite results. The effect is going to be the reciprocal of b since it is multiply. But we'll take a look at a couple of graphs. Let's turn in your workbook, please, to page 109. So I'm going to input into my graphing calculator y equals 4 minus x, and also y equals 3 times 4 minus x. And my calculator can do that work for me. I'll get a sketch on my graph, and then we'll talk about the new language of today. Now we want a description of what's happened to that graph. That graph has stretched, it's gotten taller. And it's gotten taller in the vertical direction, so that's why it's called a vertical stretch. And it's gotten taller by a factor of 3, so a vertical stretch of 3 about the x-axis. The x-axis is the one that remained the same. The x-intercepts of the graph have remained unchanged. No change on the x-intercepts. The y-intercept has changed. I've actually gone up to 0, 6, and you could find that using your graphing calculator. You could find that using your table of values. And just getting used to the format, I can read the vertical stretch off of a factor of 3 because it was written on the right-hand side. If I were to have written the equation in the other format, 1 over 3 is equal to f at x, then I have to take the reciprocal to get that vertical stretch idea. I've slid down to part 2. I'm wondering if you can hypothesize what happens when I have a half sitting out in front of the f at x. So I've got a graph that I don't really have the equation for. It's not defined by anything that I recognize. Do you recognize what that graph looks like? I'm actually still trying to make use of my f at x graph from part 1. So my f at x is still that same definition as being the square root of 4 minus x squared. Now when I hit it with a half, if I want to write an equation which represents that, I'm going to get it on my graphing calculator, and perhaps you can write the equation with the 2 on the other side. We want to practice that. So that would be 2y is equal to f at x. I'll try to fix my orientation again. So I expect that that vertical stretch can be read directly off, a vertical stretch of a half about the x-axis. If you still have your equation from before, you can simply replace the 3 with a 0.5. So I'm now graphing 0.5 times the square root of 4 minus x squared. Taking a look at my graph, and I find that my new graph actually sneaks inside my old graph, which is a little bit awkward. Let's look at that graph. Like before, the x-intercepts have not changed. So there's no change on the x-intercept. But what I see is that the y-intercept has actually dropped by a factor of a half. It used to be at 0.2, and now it's at 0.1. So now, based on what we've seen, can we complete the statement? When the a is written on the right-hand side, which is certainly convenient, compared to the graph of y equals f at x, the graph of y equals af at x results in a vertical stretch about the x-axis by a factor of a. If we replace y with 1 over ay, that's equivalent to the statement being y equals a to the f at x. So be careful, note that's possible. Get familiar with either having the a on the left-hand side or the right-hand side. Let's turn the page over. We continue to use the same graph, and we're going to graph now looking at horizontal stretches, which should be something different. Y equals 4 times x. So if you can get that graph on to the graphing paper, then we'll talk about its changes. So what happened when you graphed it? I had to be really careful that I had properly squared. So it's the square root of 4 minus bracket 4x squared. So you want to make sure that that gets in there. My graph actually has shrunk substantially. It is now sitting with x-intercepts that have altered and still going up to that same y value. So now we need that descriptor. I've affected my horizontal. So that's a horizontal stretch by a factor of a quarter about the y-axis. So the y-axis didn't change this time. That means that the y-intercepts of the graph are still the same. But my x-intercepts have changed. And those x-intercept values are at 1 and -1. Just looking at the algebra for the x-intercepts, my x-intercepts were before at 2 and -2. So I was running at 2 and -2. And now I found that my x-intercepts have changed and they've become half and -half. Half and -1/2. And what's happened there, we've got that same quarter effect. I've taken my x-intercepts and multiplied by a quarter. So 2 times a quarter gives me a half. We're still dealing with that same graph. And I want you to see if you can run the work for y equals. So y equals the square root of 4 minus 1/3 x squared. We want to get that graph in there. We want to talk about the x-intercepts and the y-intercepts and get a graph. So I had a little bit of fun making my graph actually work. Got to watch the brackets. The x-intercepts have changed by a factor of 3. They've grown. My y-intercept is still the same. So I've got this semicircle that's kind of in that format. So I've got a horizontal stretch. I've stretched horizontally. So horizontal stretch. Remember, it's an opposite for x. So a horizontal stretch by a factor of 3. About the y-axis. That's the axis that remains the same. So the x-intercepts have changed. They've increased by 3. I'm now at -6 and 6 for my x-intercepts. The y-intercepts have remained unchanged. There's no change on my y-intercept. And we get a chance to make a general conclusion here. Complete the following statement. Compared to the graph of y equals f at x, the graph of y equals f at b at x results in a horizontal stretch about the y-axis by a factor of 1 over b. It's the reciprocal. It's opposite. So we're used to that. I've got a little bit more work to do on this lesson, so I'm actually going to break it up into 2 recordings. So I'm going to stop here, and we'll start in a few minutes.